So now we will have an introductory discussion on Fourier transforms. We will see how the Fourier transform is formulated. Then we will discuss a few properties of Fourier transform. So I will need 2 sessions to complete the properties of the Fourier transform. Now the Fourier series we had discussed was used for the analysis of continuous time periodic signals. So we had analyzed periodic signals there in the continuous time domain. So the Fourier series was used for the analysis of periodic signals. Now the Fourier transform will be used for the analysis of aperiodic signals. So Fourier transform is formulated from the Fourier series as follows. So in fact, there are several approaches to arrive at the analysis and synthesis equations for Fourier transforms. What we will do here is we will use the approach that starts from the Fourier series representation of a periodic signal. To start with, let us consider x of t as a signal of finite duration as shown here. So x of t is of finite duration, let us say from minus t1 to plus t1. So this is x of t. So this is time. And now let us form a periodic signal x t0 of t, which is obtained by periodically repeating x of t with a period t0. So this is t0. So we will go on repeating this from minus infinity to plus infinity. So this periodic sequence you can call as xt0 of t. So you have to observe that limit t0 tending to infinity of xt0 t is equal to x of t. So why? Because we are taking this separation t0 to tending to infinity. So this second pulse will appear at a time instant, at a time duration that is tending to infinity. Whereas this previous cycle would be at some value that is tending to minus infinity. So in effect, limit t0 tending to infinity, x t0 of t is equal to x of t. So this is a very important observation that you have to remember here. Now, x t0 of t is a periodic signal, therefore it can be expressed as a Fourier series. So x t0 of t can be written as sigma over k ck e raised to j k omega 0 t, where omega 0 is 2 pi by t0, which is the fundamental period. Fundamental frequency, capital T0 being the fundamental period. And you can write the expression for ck as equal to 1 by t0 integral minus t0 by 2 to plus t0 by 2 x t0 of t e raised to minus j k omega 0 t dt from the Fourier series expansion. Now observe that within the limit minus t0 by 2 to plus t0 by 2, if I look at the limit minus t0 by 2 to plus t0 by 2, you see that x t0 of t is same as equal to x of t. So I can rewrite that integral as equal to 1 by t0 integral minus t0 by 2 to plus t0 by 2 x of t e raised to minus jk omega 0 t dt. Now since interval minus t0 by 2 to plus t0 by 2 is in this interval, this is because since in the interval minus t0 by 2 to plus t0 by 2 x t0 of t is equal to x of t. Now you can also write this as 1 by t0 integral minus t0 by 2 to plus t0 by 2 x of t e raised to minus jk omega 0 t dt is also equal to 1 by t0 integral minus infinity to plus infinity x of t e raised to minus jk omega 0 t dt. Why? Because x of t was your finite duration signal, and the range from minus infinity to plus infinity will involve only this finite duration sequence. So therefore, this limit from minus t0 by 2 to plus t0 by 2 can be replaced as minus infinity to plus infinity. Now, what we will do is we will define x of j omega. X of j omega is also sometimes represented as x of omega. We will give a suitable name to x of j omega or x of omega later. But however, now for the time being, we will define x of j omega as equal to integral minus infinity to plus infinity x of t e raised to minus j omega t dt, which is also defined as, it can also be represented as x of omega. So we can use either x of omega or x of j omega to represent this integral. So x of j omega is equal to, so this is something that you have to familiarize. This is something that you have to Remember by heart. So x of j omega is equal to integral minus infinity to plus infinity x of t e raised to minus j omega t dt. Now, therefore, this ck, which you had written as 1 by t0 integral minus infinity to plus infinity x of t e raised to minus jk omega 0 t dt, can be written as 1 by t0 x of k omega 1 by t0 x of k omega 0 1 by t0 x of k omega 0. So ck is equal to 1 by t0 x of k omega 0. What we will do is, now we will substitute this expression, what we have got here, ck is equal to 1 by t0 x of k omega 0 in the synthesis equation, and write x t0 of t is equal to 1 by t0 sigma over k x of k omega 0. So 1 by t0 into x of k omega 0 is your ck. So 1 by t0 sigma over k x of k omega 0 into e raised to j k omega 0 t. So here we will make the substitution that omega 0 is equal to 2 pi by t0, and we will rewrite the equation as follows. X of t0 t is equal to 1 by 2 pi sigma over k x of k omega 0 e raised to j omega 0 t omega 0. So this is the expression for x t0 of t. Now let t0, that's a time period, tend to infinity. So as t0 tends to infinity, omega 0 tends to 0, and therefore we can let omega 0 is equal to delta omega. So omega 0 can be written as delta omega, because omega 0 is tending to 0, so you can write omega 0 as an infinitesimally small value of omega, which you can write as delta omega. So x of t, so as t0 tends to infinity, x t0 of t tends to, x t0 of t is equal to x of t. So x of t is equal to limit t0 tending to infinity of x t0 of t can be written as 1 by 2 pi sigma over k equal to minus infinity plus infinity x of k delta omega e raised to j delta omega t into delta omega. So omega 0 becomes delta omega, and this k omega 0 becomes k delta omega. Here omega 0 is written as delta omega. So this, if you plot this function, so if I plot if I plot this function x of k delta omega into e raised to j delta omega t, where I let this delta omega as an infinitesimally small interval in the frequency domain. So maybe you will have a plot something like this. This is an arbitrary plot for a particular example. So here you can think of this amplitude as x of k delta omega into e raised to j delta omega t. So this is x of k delta omega into e raised to j delta omega t. So this is this value, and you can consider an infinitesimally small value delta omega. So in essence, the product of these two is the area of this square shaded rectangle. Now, when k takes a different value, you have a different rectangle. So in essence, you are computing, if you compute the sigma from k equal to minus infinity to plus infinity, in essence, what you are doing is you are computing the total area under this function. The total area under this function. So since delta omega is tending to 0, I might also replace this by d omega. And since here delta omega is tending to 0, this k into delta omega I can replace by a continuous variable omega and write this equation as x of t is equal to 1 by 2 pi integral minus infinity to plus infinity. Instead of this summation will become an integral, and this x of k delta omega I can write this as a x of k delta omega naught I can write as x of k delta omega I can write as x of omega into e raised to j omega t into d omega. So x of t I can write as 1 by 2 pi integral minus infinity plus infinity x of omega e raised to j omega t d omega. So now we will write the two equations, one below the other. One is for x of j omega. X of j omega, we started by defining x of j omega as equal to integral minus infinity to plus infinity x of t e raised to minus omega t dt, and the value that we have derived right now as x of t is equal to 1 by 2 pi integral minus infinity to plus infinity x of j omega e raised to j omega t d omega. We call this as the Fourier transform pair. So what we are doing here is we are analyzing the signal x of t in the frequency domain. In the frequency domain, we get a continuous plot of x of j omega in the frequency domain because omega is continuous. Whereas for the Fourier series, you have the line spectrum. Now for the Fourier transform, you have a continuous function of omega. So this is also represented as x of omega, as we have seen. So x of omega or x of j omega. So x of j omega is a continuous function. X of j omega or x of omega is a continuous function in omega. Omega takes all values from minus infinity to plus infinity. And this you can write as integral minus infinity plus infinity x of t e raised to minus omega t dt. So this you write as x of omega. And now here x of t, which we have derived right now, can be written as x of t is equal to 1 by 2 pi integral minus infinity to plus infinity x of j omega e raised to j omega t d omega. So here we have both the analysis. So this you call as the analysis equation, and this you call as the synthesis equation. So both the analysis and the synthesis equation are integrals. You call this as Fourier transform pair. So in Fourier transform, what you do is you analyze mostly aperiodic signals. So in this particular case, for our example, we had considered a finite duration signal. So you can compute the spectrum, that's a frequency domain analysis of such aperiodic signals, which I also will put in brackets as in general. So in general, we can analyze these aperiodic signals in the frequency domain by using Fourier transform. So x of t will have a Fourier transform given by x of j omega, where x of j omega is given by the analysis equation. X of j omega is a continuous function in omega, and here omega takes values from minus infinity to plus infinity. Now x of t is the synthesis equation. It gives you the synthesis equation. From x of j omega we can go to x of t, and it's given by 1 by 2 pi integral minus infinity to plus infinity x of j omega e raised to j omega t d omega. Okay, so this is a relation that you have to remember. So for example, I can look at some random signal. So here I choose to draw what is known as a Gaussian function in the time domain, and as its Fourier transform, you will have what is known as the Gaussian function in the frequency domain. So it's one of the rare signals which has got the same shape in the time domain and the spectral domain representation. Let us look at a square pulse. Later we will prove this. We will see that the square pulse has got a sinc function as its Fourier transform. So the square pulse has got a sinc function as its Fourier transform. So this is in the frequency domain, whereas this is in the time domain. Okay, so you see that x of j omega or x of omega is a continuous function in omega. Omega takes all values from minus infinity to plus infinity. What is omega? Omega being your angular frequency. So you cannot normally think of, so you have to have some justification for this negative frequency. The justification for the negative frequency is because you are using e raised to j omega t to analyze your signal x of t. So in essence, what you are doing is you are representing x of t in terms of e raised to j omega t, where omega takes values from minus infinity to plus infinity. Now, if you look at one e raised to j omega 0 t, so let us look at e raised to j omega 0 t. So this is a phasor that rotates in the positive direction being the anti-clockwise direction. So positive direction because this rotates in the positive direction. So I'll draw that once again. So I have drawn the two-dimensional plane. Let me consider a phasor. So to represent the phasor, I will use a different color. So this phasor is rotating in the positive direction with an angular velocity of omega 0. This length is equal to 1. So this phasor is a representation for e raised to j omega 0 t. Now, if the same phasor is rotating in the negative direction, so let me look at another phasor that rotates in the negative direction. So negative direction will be the clockwise direction because the frequency increases from 0 degree to minus 90 degree to the angle 0 degree to minus 90 degree to minus 180 degree to minus 270 degree to 360 degree. Here it increases in the positive direction. The angle, which is omega 0 t, increases from 0 to 90 to 180 to 270 to 360. Whereas here the angle increases in the negative direction from 0 to minus 90 to minus 180 to minus 270 to minus 360, etc. So you can have omega 0, which is the angular frequency or angular velocity of this phasor, which is measured in radians per second. So it is measured in radians per second. And it can take both positive values or negative values depending on the direction in which the phasor is rotating. So you know omega is equal to 2 pi f. So omega by 2 pi will give you f, that is the frequency. So when omega is positive, the frequency is positive, and when omega is negative, the frequency is negative. So which means in theory, at least for the complex exponential, you can think of a signal of frequency, let's say minus 1 kilohertz. That is possible. You cannot picturize a signal of frequency minus 1 kilohertz from your function generator. From the function generator, you have positive valued frequencies. Whereas at least on paper, at least for a complex exponential, at least for these kind of phasors, you can picturize signals that are phasors rotating in the negative direction and therefore having negative frequencies. Okay, so that's about your Fourier transform pair. So now what we'll do is we'll move on to the magnitude and phase spectra of the Fourier transform. So x of j omega you can write as equal to modulus of x of j omega into angle of x of j omega. Now it's easy to prove, and the proof is so very trivial, so I'm not going to prove that here. It's very similar to how you prove the corresponding property for Fourier series. When x of t is real, you can write x of minus j omega. So you only need to write these analysis equation for x of j omega and then replace omega by minus omega to get x of minus omega. So when x of t is real, you can write x of minus j omega is equal to x conjugate of j omega. So the proof is very trivial. So which means modulus of x of minus j omega is equal to modulus of x of j omega, because modulus of conjugate of x of j omega is same as that of modulus of x of j omega. So which means you see that the magnitude spectrum is symmetric, whereas the angle of x of minus j omega is the angle of x star of j omega, which is therefore minus angle of x of j omega, which means the phase spectrum is antisymmetric. So magnitude spectrum is symmetric, phase spectrum is antisymmetric. This is when you say it has got conjugate symmetry. So let me look at the real parts and imaginary parts. So if I write x of j omega is equal to a of omega plus j into b of omega. Then for a real signal, this is conjugate symmetric, which will mean that a of minus omega is equal to a of omega, and b of minus omega is equal to minus b of omega. So this is a fallout of the conjugate symmetry of x of j omega. It's easy to prove. We will look at now the Dirichlet conditions, which are sufficient but not necessary conditions for existence of Fourier transforms. Just like we have the Dirichlet conditions for the Fourier series, now you have the Dirichlet conditions for the Fourier transforms. So Dirichlet conditions are, as before, they are sufficient but not necessary for the existence of Fourier transforms. So if you have a signal that satisfies a Dirichlet condition, definitely it means that a Fourier transform will exist. And you can also have signals that do not satisfy the Dirichlet conditions but having a Fourier transform. We will see examples later. For example, we will look at some periodic signals having Fourier transform representations also. And signals that consist of several impulses also will have Fourier transforms. And we will see that such signals do not satisfy the Dirichlet condition but still have a Fourier transform. We will see examples later. So the Dirichlet conditions are three in number. See, the first one is x of t is absolutely integrable. Previously, we had written that one cycle of x tilde of t is absolutely integrable for the Fourier series. So here we write x of t is absolutely integrable. So which means integral minus infinity to plus infinity. Modulus of x of t dt is less than infinity. So mind you, this does not mean that x of t has to be finite duration. So it is obvious that when x of t is of finite duration, then the signal is absolutely integrable. But there are cases where x of t is not of finite duration and is absolutely integrable. For example, you can look at an exponentially decreasing function. This is an exponentially decreasing function. We'll call it as e raised to minus at into u of t, because it is one-sided. And you will see that this function is absolutely integrable, because you can find out integral minus infinity to plus infinity e raised to minus at into u of t dt, which we can write as integral 0 to infinity, because u of t exists only from 0 to infinity, integral 0 to infinity e raised to minus at dt. So this we can evaluate, because this is e raised to minus at by minus a, and you put t equal to 0, t equal to infinity and t equal to 0. So that will give you the answer to this. So this you can evaluate. So you see that this is not a finite duration, because it dies to 0 only at infinity. So the first Dirichlet condition, which states that x of t has to be absolutely integrable, does not mean that x of t has to be of finite duration. So if x of t is of finite duration, then it is definitely absolutely integrable. But for a signal to be absolutely integrable, it does not mean that it is of finite duration. I hope it's understood. So integral minus infinity to plus infinity, modulus of x of t dt is less than infinity. Now, the second Dirichlet condition is the same as that of the previous case. X of t has a finite number of maxima and minima within a finite interval. We had seen illustrations in the previous class. Then x of t has a finite number of discontinuities within any finite interval, and each of these discontinuities is finite. So x of t has finite number of discontinuities within a finite interval, and each of these discontinuities is finite. So these are the Dirichlet conditions, which are sufficient but not necessary conditions for the existence of Fourier transforms. Now we will look at a few properties of the Fourier transforms. In fact, we will only look at 5 or 6 properties in today's class. We will continue with the other properties of Fourier transforms in the next session. So the first property, so all the properties assume that x of t is a signal, a periodic signal, or any signal that has got a Fourier transform given by x of omega. So x of t has got a Fourier transform given by x of omega, or you can also write this as x of j omega, x of omega or x of j omega, right? So the first property, the proof is very trivial. It states basically the superposition theorem. So suppose you have a Fourier transformer Fourier transformer is a device that performs Fourier transform. So let me give x1 of t at the input of the Fourier transformer. I will get x1 of omega at the output. So that is your Fourier transformer. It performs Fourier transform of x1 of t. Likewise, let us look at x2t as the input to the Fourier transformer. It will perform the Fourier transform of that to give you x2 of omega. So if x1t gives you x1 of omega, and if x2t gives you x2 of omega, and if a1, a2 are constants, are scalar constants, then a1 x1t plus a2 x2t will give you a Fourier transform given by a x1 omega plus a1 x1 omega plus a2 x2 omega. So this is the superposition theorem that is stated here. So when the system obeys superposition theorem, that's when you say the system is linear. System is linear. Now, the second property is the time shifting property. Again, the proof is trivial, so I'm not proving that here. So time shifting property states that if you have x of t having a Fourier transform given by x of omega, then x of t minus t0 will have a Fourier transform given by e raised to minus j omega t0 into x of omega. So if you take the spectrum, magnitude spectrum of this signal, this composite signal, you see that the magnitude of this phasor is equal to 1. So it's basically magnitude of x of omega itself. So the magnitude spectrum after the time shifting remains the same. However, you see that there is an additional phase shift of e raised to minus j omega t0. So to the original phase spectrum of x of omega, you have to add the additional phase shift of e raised to minus j omega t0. So anyhow, that is very easily understood because x of t minus t0 is not going to change the frequency contents, except that it will introduce an additional phase shift because of the time delay here. So magnitude spectrum after time shifting remains the same. There is an additional phase shift of e raised to minus omega t0. Then you have the frequency shifting property. Frequency shifting property, the proof is again trivial. So it's in fact very similar to the time shifting property. Here you have a complex exponential multiplying the spectrum. Now we will have the complex exponential multiplying the time domain signal. So let us multiply x of t by e raised to j omega 0 t. So x of t multiplied by e raised to j omega 0 t, this is sometimes called as complex modulation. This is sometimes called as complex modulation. As you have seen in I'm not very sure whether you have studied analog communication. So you have seen that if I multiply x of t by a cos omega ct, cos omega ct, I should have written this as cos capital omega because that's your continuous frequency. Cos omega ct, this you call as the carrier frequency. Then this corresponds to what is known as double sideband suppressed carrier amplitude modulation. So here what you have say for example, if x of t has got a spectrum like this, then after double sideband suppressed carrier modulation, you will have a, so if I multiply this by cos omega ct, then you will have a lower sideband and then upper sideband. You have a lower sideband and an upper sideband. So the spectrum is shifted in the frequency domain. Okay. So likewise, instead of multiplying by cos omega ct, if I multiply by e raised to j omega ct, we call this as a complex modulation. It's called as complex modulation. So in fact, I don't want to diverge too far because this we will study in another subject. Okay, so in case you want further clarification, you can ask that question before we start the next live session. So I can explain that way. So the frequency shifting property states that e raised to j omega 0 t into x of t is Fourier transform to x of omega minus omega 0, which means the Fourier transform x of omega is shifted by an amount omega 0. The proof is trivial. It's just like the proof for time shifting. I have not given the proof for time shifting as well. But however, you have done the proof for a similar property of the Fourier series. So I will leave that to you to prove the properties. So multiplication by e raised to j omega 0 is called as complex modulation. This results in shifting in the frequency domain. Say for example, if I have this as my spectrum for x of t, if this is a spectrum for x of t, then if I multiply this by, so I will put this as omega 1 and this is minus omega 1. So it's a spectrum of a real signal probably, because the magnitude spectrum is symmetric. Phase spectrum I have not drawn here. This could be shown as anti-symmetric, so that will be a real signal. Now the spectrum of e raised to j omega 0 t into x of t would be like this. So this will be omega 0 and this would be now centered around omega 0. It's shifted by omega 0. Now this property is known as the dual of the time shifting property. You will see what is the duality property later. Dual of the time shifting property. So you can understand why it's called as a dual. Whatever was there in the time is now there in the frequency and vice versa. So this is the dual of the time shifting property. Okay. So that's the frequency shifting property. Now you have what is known as the time scaling property. Time scaling property states that for a real constant a, and mind you, a can be both positive or negative, then x of at will result in a spectrum given by 1 by modulus of a into x of omega by a. Now let us look at what is x of at. You have done a similar problem. You have seen a similar property for the Fourier series coefficients, but however the result is very different here. For the Fourier series, if x of x tilde of t had a, I'll write the corresponding property here. For the Fourier series, you had seen that if x tilde of t had got a Fourier series coefficient given by ck, then x tilde of at will have the same Fourier series coefficient given by ck, except that if these were separated by omega 0, these would be separated by omega 0. But if these were separated by if the period here is equal to t0 here, the period here would be equal to t0 by a. That's the fundamental period. The fundamental frequency here would be omega 0, and the fundamental frequency here would be a omega 0. So that's only difference. Fundamental frequency would be a omega 0. So if this is separated by, if these lines were originally separated by omega 0, you will basically have the same lines that are separated by a omega 0. Unlike the property for the Fourier series, you have a different expression here given by 1 by modulus a x of omega by a. So x of at has got a Fourier transform given by 1 by modulus a x of omega by a. So this shows that the scaling in the time domain by a will result in an inverse scaling by 1 by a in the spectral domain. So let us look at what is scaling by a. So for example, let me look at sine omega naught t, and I can look at sine 2 omega naught t. So one cycle of sine 2 omega naught t will have half the duration of sine omega naught t. So when a is greater than 1, I see that you have a compression of the signal. For example, I'll draw an x of t here. So x of t is from, let us say, -2 to +2. So if this is my x of t, this is my x of t, then I can write x of 2t as a compressed version of this signal. So x of 2t would be from -1 to +1. -1 to +1. And x of t by 2. So likewise, I can look at x of t by 2. X of t by 2 would be from -4 to +4. So -4 to +4. This is -4 to +4. So when t is greater than 1, you have a compression, and when t is less than 1, you have a expansion. Okay. So that is time scaling. So that is scaling in time. So the equivalent frequency domain will be inverse scaled by 1 by a in the spectral domain. So scaling in the time domain by a results in an inverse scaling, that is by 1 by a in the spectral domain. If modulus a is greater than 1, the compression in time, you have compression in time and expansion of the spectrum. If modulus a is less than 1, you have expansion in time and a compression of the spectrum. So the proof is shown here. The proof is trivial, but I have chosen to prove that here. So proof for positive a. So Fourier transform of x of 80 I can write as integral -∞ to +∞ x of 80 e raised to -j omega t dt. So let me put at is equal to t dash. So a dt is equal to dt dash. When t takes value -∞, t dash will be -∞. And when t is +∞, t dash is equal to +∞, because a is positive. So in terms of t dash, I can write this integral as integral -∞ to +∞, x of t dash e raised to -j omega by a t dash dt dash by a. So I will take this 1 by a outside and write as 1 by a integral -∞ to +∞. So t dash I might replace by t as well, because it's a finite integral. So t dash or t are only dummy variables. They will vanish when you evaluate the finite integral. That's when you evaluate the definite integral. So 1 by a integral -∞ to +∞. Instead of t dash, I will put back t. So this is x of t e raised to -j omega by a t dt. So which you can write as. So what is this expression? So if this had been omega alone, I would have written this as x of omega. Now instead of omega, I have omega by a. So I write this as omega by a, x of omega by a. So this is 1 by a into x of omega by a. Okay. So now for a less than 0, at is equal to t dash, dt is equal to dt dash, a dt is equal to dt dash. So t is equal to -∞, t dash is equal to +∞. Why? Because a is negative. When t is equal to +∞, t dash is equal to -∞. So this integral now becomes 1 by a integral infinity to -∞, because you have a as negative, x of t dash e raised to -j omega t by a e raised to -j omega t dash by a dt dash. Right? Because t is equal to t dash by a. So this you can write as, I will take this reverse signs in the definite integral. I will write this from integral -∞ to +∞, and take the resultant negative sign to the bottom of the denominator. So this becomes 1 by -a integral -∞ to +∞, x of t dash e raised to -omega t by a t dash by a dt dash, which is equal to 1 by -a into x of omega by a. I can write this as 1 by -a into x of omega by a, because this evaluates to x of omega by a. So you previously had, when a is positive, 1 by a x of omega by a, and when a is negative, you have 1 by -a into x of omega by a. So which I can combine and write as 1 by modulus a x of omega by a. And we have a very fairly straightforward fallout of these scaling property Fourier transforms, which is for time reversal. So the time reversal property is very easy to prove. It's a special case of the scaling property. I only need to put a is equal to -1. So you know that x of at is Fourier transform to 1 by modulus a x of omega by a. So let me put a is equal to -1. So this becomes x of minus t is Fourier transform to what? 1 by modulus a is 1 by modulus of -1. So this is 1 itself. X of omega by -1 is x of minus omega. So this is Fourier transform to x of minus omega. X of minus t is Fourier transform to x of minus omega. So this is the time reversal property of Fourier transform. Okay, so we will stop for today, and we will continue with the rest of the properties of the Fourier transform in a later session. I already have a few slides that I have taken the previous semester. So next class onwards, I will be using such slides. Okay, we'll stop this for today. I request you to go through the properties before we have another recorded session in the next class, which is about the remaining properties of the Fourier transform. Okay, thank you.